So our second speaker today is Jim Lewis of SynthWorks Design Incorporated. He's a VHDL verification specialist with 30 plus years of design and teaching experience. He's the chair of the IEEE 1076 VHDL Standards Working Group. He's the chief architect of the open source VHDL verification methodology, often referred to as OSVVM. He is an expert VHDL trainer for SynthWorks Design Incorporated, and in his design practice, he has created designs for networking, fighter jets, video phones, and spacecraft. He's based in the US, so we thank you for getting up early today. And the title of his talk is OSVVM in a nutshell, VHDL's #1 verification methodology. Over to you, Jim.
Okay, thanks, Mike. So let's start out. What is OSVVM? So OSVVM is a verification framework, just like System Verilog and UVM is a verification framework. It's a verification utility library that gives VHDL advanced verification features such as constrained random, functional coverage, and requirements tracking. We have a verification component library. We have a scripting library that gives us tool-independent scripts, basically one script to run any of our simulators. We have a co-simulation capability that allows us to run software in our hardware simulator, such as writing tests or booting code in your VHDL simulator. And we have a test report generator that generates HTML test reports for humans and JUnit XML for the continuous integration tools. OSVVM is free open source. It's used by approximately 50% of FPGA designers worldwide. And it's developed by the same VHDL experts who have helped with the VHDL standards. If we take a peek at the OSVVM verification framework, again, it looks just like System Verilog. We have verification components to implement interface signaling. We have a test sequencer, which calls transactions, which is where our test case is. Each test case then is a separate architecture of this test sequencer. If we look at the framework, it's nothing more than structural code, just like you do in RTL design. So we have things like an instance of the DUT, we have instance of the verification components, and we have an instance of the test sequencer. So if we go back to the elements of the verification framework, we have a transaction interface, which is a record, a transaction API, which is procedure calls that allow us to dispatch transactions. We have the verification components, and we have the test sequencer. So we're going to talk about all of this in this presentation. Okay, so first, our easy approach. Our easy approach came from this observation. Some interfaces do the same sort of transactions. So we've currently classified things as address buses or streaming interfaces. So address buses like AXI4 and Avalon do read and write transactions. Streaming interfaces like AXI, Stream, and UART do send and get type transactions. For these interfaces, then, the OSVVM model independent transaction library defines the transaction interface and the transaction API. So, and it looks a little bit like this. So we have a record in there, and the record uses types from the OSVVM library so that we can use those as in-out to our design or to our verification components. And then it has the transactions like write and read. This is very, very brief subset. We also do things like bursting and that sort of stuff. For the stream, it's the same story. We create the record, we create the transactions. Okay, so benefits of this then. We accelerate verification component development because you use the transaction interface and API defined by the model independent transaction library. Hence, we get to focus on writing verification component behavior, and our basic verification component is as simple as writing a procedure. So there's no reason to start with something simpler. This is it. We accelerate test case development because similar verification components use the exact same transaction API. And hence, you can share transaction sequences between similar verification components. Co-simulation is supported because OSVVM co-simulation supports all model-independent transaction verification components, including ones that you write. And you can thank Simon Southwell for this because he's the one that developed that part. And it accelerates accelerates your documentation of your verification component because you really only need to identify the transactions you support and then refer to the OSVVM user guides where there's more details on those transactions. Okay. Our verification component entities, we have the DUT interface, which may be individual signals or maybe a record, as I've done here on the ASIC4 interface. The transaction interface is always one of the two record types we talked about previously. Then inside a very, very basic verification component, we start with this wait for transaction. Okay, this collaborates with a transaction API that puts things into the record and then signals it through incrementing ready. And when ready increments, wait for transaction wakes up. It has been blocking up to this point. It wakes up, decodes the transaction, and then we go and do that transaction. So if it's a write operation, we do things appropriate for a write operation. I've kind of suggested that we call a procedure here, but this is generally where I write code. Okay, so benefit here. Coding OSVVM verification components is well within the capability of any VHDL engineer. If we look at the test sequencer, then what we're going to see primarily is these transaction interfaces as the ports. And then internally, we're going to see the whole test in this file. So unlike System Verilog, it's not spread out across multiple files with constraints in different places. We have a control process, which is in charge of initialization, finalization of the test. We have one process per interface, so we're concurrent, just like your design is concurrent. We build tests by calling transactions, which makes it easy to add in and mix directed testing with constrained random testing, and then also add in other features such as scoreboards and functional coverage. But because we are running independently, we need synchronization primitives. So we use this wait for barrier. It basically blocks, when a process hits it, it blocks until all processes hit it. So this gives, for example, the AXI manager a chance to set up the DUT before the TX starts spewing data at it and stimulus at it. We also use it as our test done indication. That gives us a lot of flexibility. The control process doesn't need to know when the other processes finish. They just finish, they signal test done, and then the control process will finalize the test. One of the steps in finalization is error reporting, which we accomplish by this end of test reports. Okay, so it's assuming that you've been doing checking along the way. Okay, so if you look at the test sequencer, the first thing you're going to see is a bunch of ID declarations inside of it. And these are all IDs that reference into OSVVM singleton data structures. So this is the container for them. We initialize the test. We open our transcript and potentially set up mirroring, so we write to console. Then we call new ID to construct these to say, hey, give me one of these things to the data structure. And then perhaps we enable our logs and message filtering. Okay. And then we wait until the test is done. Or in this case, if 5 milliseconds go by, that's our watchdog timer on the whole test. So this will wake up in 5 milliseconds, whether we get test done or not. Then we get into a test case. So a test case is calls to our transactions, such as send, get, and check. Also using OSVVM's affirmations for self-checking. The affirmations are just basically our checkers. Okay, so we do a send transaction that sends something to the DUT. And then coming out some other interface, we do a get transaction to receive things. Okay, coming out of the DUT. And then we do affirm if equal, check the value we received against the value we were expecting. So that's one place we could be doing a check. Or we could push the check off into the verification component, given that the verification component has implemented this transaction, and ask it to do the checking internally to it. So we're giving it the expected value. It does the checking inside. Basically, then our affirmation, signal, pass, fail, as well as count errors and count the number of checks we've done. because the number of checks we've done is an indication of quality of the test. A test without checks, you shouldn't be reporting that as failed. We'll deal with that in a second. Okay, so if we pass, we'll get a log pass, and then we'll get this message in TV. This gives you the context. Where did it happen at? So when we do the new ID on the IDs, we gave it a name. That name prints here. Okay, so we pass. We only print what we received. We fail. We print both the received and the expected. Okay, benefits. We've improved readability, and we've greatly simplified writing self-checking tests. Now, OSVVM also has requirements tracking. For requirements, affirmations also count errors and checks. Okay, so you saw we opened a rec ID on the previous slide. We can use that directly, or we can say affirm if and the name of the ID. That'll create the ID on the fly and then use it. Okay, and then key point here, a failed requirement becomes both a requirements failure and a test failure. Okay, so we pick up back in the control process. So either we finish due to test done, everybody hitting test done, or 5 milliseconds go by. So if 5 milliseconds go by, we need some indication that the test timed out. So we just simply check. We do an alert. Alert is one of our checkers. It's not a pass-fail check. It's just a fail check. Okay, so alert if now is greater than or equal to 5 milliseconds because then we timed out. Then we close our transcript and we check our current transcript against the transcript in our validated results. So we get to get some checking there. Then note these start with double quotes. So these are not IDs, these are requirements. So we're checking, is the test self-checking? So we're going to check our firm count. Is it greater than 0? Okay, or is it greater than 1? Since we just did an affirmation, we want to know if the check itself had any checks in it. Okay. Then we can check and see that the test is reached 100% functional coverage. And then we can check and see and add a requirement that the test passed. Okay. And then we'll report everything. This end of test reports is an essential part of, is the first step of OSVVM creating its reports. And we'll talk about OSVVM reports in a few minutes. Okay, so constrained random testing. So this is a layer replacing the simple test we just did. Okay, so constrained random in OSVVM is very simply a code pattern plus randomization plus transaction calls. In here, we have a weighted distribution. In a weighted distribution, we have 5 different values in here in this 2 sets of parentheses. That means the internal parameter is an integer vector, and it's going to have a range from 0 to n-1, where n is the number of elements we have. So it's going to go 0 to 4. And then these numbers add up to 100. So the 70 is going to be 70 out of 100 times we're going to generate a 0, the index that corresponds to that. Okay, so 70% of the time we're going to get this first test case. We're going to set up our nominal checking here. 10% of the time we're going to inject an error. So we're going to set up that error injection here. And then we do our transaction. So we could be doing our transaction here, or we could be doing our transactions in our case branch, which would allow us to do multiple transactions or different numbers of transactions in each step, if that was a thing we needed to do. Okay, and again, that's just one of the patterns OSVVM uses for constrained random. Now, how do we check it? Okay, so we can check it by repeating that pattern, but that's tedious and error prone. We don't want to be doing that. Okay, and then we have scoreboards. So what we're going to check it with is scoreboards. And we can simplify self-checking when the data is minimally transformed. So it's going through like an Ethernet switch or something like that. So internally, a scoreboard is a FIFO plus a checker. We use package generics to support different types. And we support a match function, which allows us to handle small data transformations because the match function defines what equality means. We handle out of order execution and we handle drop values. So using scoreboards, we set up the ID and we allocate the new ID for it back in the control process. And then here we simply push a value, expected response into the scoreboard, and then we send a transaction. And then on the receive side, we get the transaction, and then we check that transaction against what's in the scoreboard. So we're sending what we receive to the scoreboard, and internally, the scoreboard checks it and basically posts an affirmation against it. Okay, so the benefit here, the checker process, RxProc stays the same, even when the generator process changes. Okay, the next thing we might add is functional coverage. Functional coverage tracks that items in your test plan happen. So we're tracking requirements, features, and boundary conditions. Why? Well, with randomization, do you really know what the test did? Sometimes no. So functional coverage plus code coverage at 100% is our indication that we got it. Okay, so functional coverage can be divided into two different pieces, item coverage or cross coverage. Item coverage looks at a single item and does things like binning. So if we're looking at like a transfer count and we want to know that we've tested that transfer count, we're worried about that transfer breaking at small transfers and big transfers. We look at those individually. So 1, 2, 3, 253, 254, 255. And then the middle range from 4 to 252, we kind of take it as a big aggregate. 2, as I've done here, maybe up to 4, but probably not more than that. Cross coverage is about tracking relationships between independent objects. So we got 2 inputs to an ALU. Each can select one of 8 registers. Has each register from input 1 been used with each register of input 2? We need to make sure our selection has that capability. Okay, why not just do code coverage? Well, code coverage tracks code execution, but it misses anything that's not in the code. This binning is not in the code. Tracking independent inputs, that's not in the code. Okay, so setting up code coverage in OSVVM, again, we're going back to our ID types, which are part of our singletons. We do a new ID to get an ID, which allocates stuff in our package to create the data structure. And then we add things to the coverage data structure, and we collect coverage with iCover. Pretty simple. In fact, functional coverage with OSVVM is as simple and concise as language syntax. Okay, we go a step further. OSVVM's intelligent coverage randomization is basically randomization using the functional coverage holes, or it does a random walk across the functional coverage holes. We set it up the exact same way we set up any other coverage model, but we also add coverage goals here. Here, I have them adding up to 10,000, our coverage goals. They're used as random. Once they've reached that goal, they don't randomize anymore. Okay, then we do get rand point to get a random point from the coverage model. We decode that with a case statement, exactly the same thing we were doing in the constrained random case. And then we cover it. Okay, the difference between this and constrained random is this is an exact thing. If we're looping 10,000 times, we've set up our coverage goals to add up to 10,000, then each one of them is going to be done exactly the number it's requested. Whereas with constrained random, it's not an exact thing. It takes an average of n times the natural log of n to generate n unique test cases. So this intelligent coverage does introspection of the coverage model and goes well beyond what System Verilog does. Okay, the next thing we're going to talk about very briefly is our scripting. Our scripting is basically a procedure-based API that runs on top of Tickle. So we use library to activate a library. We use analyze to compile things. We use simulate to simulate things. The benefit, it's just like a list of source files, except we also get the power of Tickle behind the scenes. We also remember things like the library settings, okay? And that also applies to you Verilog guys who get plagued with that terribly long library switch, okay? We don't have to do that in OSVVM. Paths are relative to the script location, hence we can move the directory structures around as we need to for the project. One simulator script API for GHDL, NVC, Aldec, Siemens, Synopsys VCS, Cadence Excellium, and Xilinx XSIM if you're using 2023 02 and beyond. Okay, we've got the utility library working under that. They still have some Xilinx particular issues with other stuff. Calling scripts is done either with build or include. Build is for your command line entry. We say build to start things in the simulator. Include is for inside your scripts. We call the files that we call .pro because it requires that procedure layer on top of Tickle. Okay, so again, this is the magic. Using build and include rather than source and do is the magic that makes these paths relative. Also, due to people's complaints, OSVVM also supports argc and argv. Okay, whether you need them or not is another matter to be discussed. Okay, the last thing we're going to talk about is our reports. We have an on-match test report capability. We're going to see many of these except for the test case reports. If you want to see everything, go to our GitHub site, our osvvm.github.io, go to the reports page, and on the reports page, you'll find 3 sets of these that are active. Okay, so the first message you're going to see, if you call end of test reports, it's going to generate this. And by the way, end of test reports is required for everything. Okay, everything else that we're going to see too. Okay, so it either gives you a done, passed, or a failed. And if it failed, it's going to elaborate the alert log data structure and tell you where the errors are. Then we have our mini report. Okay, so this runs, if you run a build and it's running multiple simulations, it's going to give you pass failed across all the simulations. But then we also create this HTML version. So the mini report tells you whether you need to open the HTML one or not. So if it passed, you probably don't need to open it. But in here, we have additional information. We also have links to your HTML, your log file, your HTML version in a log file. We have a link to the code coverage results. If you ran your design with code coverage, if you ran it with requirements tracking, you'll have a link to that too. OSVVM then breaks our test cases into test suites. And so like AXI-full and UART and that sort of thing. So the first thing our report has is a summary of the test suites, the test suite pass fail. And then we have our test case summaries where we list out each individual test case. And yes, each place you see the blue with the underline, that is indeed a hyperlink so that you can jump around in the file very quickly. Now, if you're debugging a regression run, this is what it's going to look like. You'll see failed up top, and then you'll go down to your test suite summary, and you'll see failed here and on a particular suite. And then you can go down to that, press the hyperlink, go down to its test case summary, and find the failing test case. And as that's been mentioned, 25% of your time on a project is spent during debug. This is the first step to accelerating debug on a big regression run. Our requirements report, we do an HTML plus a CSV report. We basically automatically, when you run with requirements, it keeps a requirements report for each test case. And then when the build finishes, it merges them all together. And then we create this HTML table as well as our CSV list. Okay, so if there's a requirement that's in multiple test cases, they get merged. But each test case can never contribute more than its goal. Okay, so it is thresholded by its goal, and then we sum them all up and we get the number passed. But any failure in a given requirement at any test case causes an overall merge failure, a failure at the merge point. Now, we also HTMLize your log file. Why did we do this? Well, if you look at OSVVM's 700 and some test cases, generates a 180,000 line log file. So this makes that file scannable basically for every OSVVM step. We've hidden the things that go below it. So you see the triangle anywhere in an OSVVM report. If it's pointing to the right, there's stuff hidden. If it's pointing down, it reveals stuff. And it's an HTML thing. You can just click on it and it rotates. Okay, so for any test case that fails, we grab that failure from the details and we factor it out, and we've also presented it again here. So it's in the report, but it's also repeated here. Okay, so we quickly can find the errors, even if we just scan this file. Also, if you click on one of those, this is what it would look like. It would reveal the exact running of that test case and show you the errors that happened during that test case. Okay. And you can also, there's also a way to get at this exact view if you go into one of our test case reports. Okay, getting OSVVM, you do a get clone recursive because OSVVM has submodules, or you get the zip file from osvvm.org. Running OSVVM scripting environment, you've got to run our startup script. More details are in our user guide. Building things, build $OSVVM libraries and in osvvmlibraries.pro. I've heard a lot of chat about accelerating the analyze step of your simulators and stuff. We're compiling or analyzing hundreds of files in here, and it runs in most simulators between 20 and 40 seconds. Okay, I don't think I need those things. And then we build and we run all our tests. So OSVM has a run all tests and a run demo tests, as do most of our verification components. So wrapping up then, OSVVM gives you a powerful, concise capability that rivals other verification languages, including System Verilog and UVM. We have an on-match reuse through the entire verification process. We have an on-match report capability with our HTML for humans and JUnit XML for continuous integration tools. By the way, the HTML we generate is quite a bit better than what you'll get on a JUnit. Test cases are readable and reviewable by all and adopted incrementally as needed. Tests and verification components can be written by any VHDL engineer with a good verification lead. So you can move your engineers around on your projects. Just a quick infomercial. We provide a training on OSVVM, our advanced VHDL test benches and verification class. This is our OSVVM boot camp. We offer it worldwide. Okay, thank you for attending, and I'll turn it back over to Mike.
Brilliant. Thanks, Jim. And again, thank you for finishing on time. That always helps. Yeah, we have one question, or a few questions online. The first one is, with the barrier mechanism, can you wait for 3 out of 4 processes to reach the barrier rather than wait for them all, please?
Not yet. I'd need to see a use model for it, but we have that underneath the hood. We have that capability. It would be fairly simple to do, but we would need to know the use model for it so that we do something sensible rather than a bunch of things that we have to support because we created it.
Okay. A second question is, we currently use an in-house methodology. What can I say to management to convince them about OSVVM, please?
Yeah, right. So if you look at some of the statistics, you're investing heavily in a methodology, and there's around $1 million investment in just OSVVM. Maybe not a million, maybe I think it was $500,000. If you look at Black Duck, I think it is. And so it is a heavy investment. OSVVM is very straightforward and simple to use. So.
Okay. And what is the best way to learn OSVVM?
Of course, we provide complete documentation on our websites, but the best way is to take a class. It's a weak investment, but it's a huge. It's like getting launched in a slingshot. It's a huge jump start into the flow.
Okay. And just maybe just a couple of bullet points. What differentiates OSVVM from other approaches, would you say?
From
other verification approaches.
Right. So, well, it would be the last point I have here. Any VHDL engineer can do OSVVM with a good verification lead. That certainly can't be said about System Verilog and UVM. UVM is a huge investment in learning. So, and I would say the other big thing about OSVVM is we use singleton data structures. That's what allows us to get the reports that we have. You have to be able to, when the test finishes, you have to be able to elaborate the entire data structures. And if you can't do that, you're not in the game. You can't generate the reports. It's just not possible. So.
Okay, brilliant. Well, thank you for your time, Jim, and appreciate your time. So I will switch
Absolutely.
back.
Thanks for inviting me.
Yeah, no, brilliant. Thank you. I will switch back to sharing my screen.
Yes, Mike.
Tell me when you can
It's
see
loading.
it.
It's a black screen. Yes, now we can see.
Okay. So again, thank you to the participants for joining today, and thank you to our two speakers, Espen and Jim. And of course, thank you to our sponsors, Agnesis, Becker, Cadence and Synopsys, and TestSolve. These presentations, both the slides and the recordings, will be put on the TestSolve DV Club webpage. You can see it there. We'll be sending you an email following up on this that has that link in, so it's easy to access both the slides and the recordings from today. As I said, we listen to our members, people who join these events. So somebody asked us with this VHDL, and although our agenda for the year was full, we added this extra VHDL content. And I think, yeah, I mean, it's quite unique that we can get both UVM and OSVVM into a single DV club. So we thank both Espen and Jim for being flexible on that. Just to show you what's coming up, if you're interested in any of these topics, 23rd of April is our informal verification. That's again another suggestion, and so is low power verification on the 3rd of September, a suggestion from one of the people who attend these. 26th of November is our other date, which we've got penciled in. And again, feel free to make suggestions for that date on the 26th of November. DV Club India has started again. And we have a talk on 28th of May on ISO 26262 compliance. 2nd of July is on chiplet-based systems. 15th of October is TBD for India. And of course, our two big one-day conferences, 18th of June 2024, Reading University. In the UK, you can either be attend that physically or online, again, both for free. And we have VHDL track in that event as well. So if you're interested in VHDL, by attending today, you can get more information on VHDL verification at that conference. And 12th of September, we are running again in Austin, in the US on the 12th of September 2024, again, physical and online. So is there a question? Okay, so we're finished there. Again, thank you for joining. Thank you to our two speakers, Espen and Jim. And we'll see you at the next DV Club on formal verification on the 23rd of April. Thank you.
Thank you, Mike. Thank you, Jim. Thank you, Espen. And thank you, everyone, for joining today's session.